If you finish your review guide and you're ready for a little bit of a challenge or a new concept, we're going to do a quick tutorial on how to calculate radioactive decay in terms of its half-life. And first of all, what does radioactive decay mean? Some of you have actually seen two types of decay, which would be known as beta and alpha. There are other types of decay, but those are beside the point for now. But those decay types signify the decay of an unstable atom to a stable isotope. So basically, decay just means you're an unstable isotope and you want to become stable. So when you're doing that, that's what decay is. It's not you just like disappearing, but it's you changing into something else. And so when we get to radon 222, for example, we're observing that its decay rate is 4 days. Now, what does that mean if it's called a half-life and its decay rate is 4 days? What a half-life is if you have, say, 800 grams of radon 222. Half-life means that it takes 4 days for that 800 gram sample to decay down to 400 grams. So your half-life is the time it takes for a sample to divide by 2, or to become half of its original amount. So it's a set rate that we can measure the decay of an isotope. And so what we do is we look at different isotopes here, and they have different rates, ranging from 4 days to 24,120 years or greater. So what we're going to do is do a sample problem for half-life. We're going to tackle number 11. So number 11 says if we start with 8,000 atoms of radium-226, how much will remain after 3,200 years? So we have to identify 4 variables for every half-life problem we attempt. And they are the time that it takes in total, or TF, final time, time of half-life, mass initial, or your initial value, and your final mass, or MF. So what we're going to do is make sure we got equal signs for all these guys, and we're going to identify our variables. So our final time is going to be how much will remain after 3,200 years in total. So that's going to be 3,200 years. And your time of half-life, we plug it into the chart. So for radium-226, we go to 1,600 years. So then we go back, right, 1,600. And then we got to get, we have to identify our initial mass and our final mass. Our initial mass says 8,000 atoms. So it could be in grams, it could be atom numbers. The problems will give you different initial masses. And then your final mass, we don't know that yet. We have to figure that out. So how you solve a half-life problem is the easiest way is to set up a chart. There is a mathematical formula you can do, but I think the chart is just the easiest, most practical way to do it. The chart will be divided into 2 columns, and in your 2 columns you'll have time for T, and then you'll have M for mass. And then what you're going to do is time will always begin, always, in every single half-life problem, at 0. Time always begins at 0. Your mass value that you'll start at will be your initial mass, or MI, and that is 8,000 atoms. So we come over here, we write 8,000 atoms, and all you got to do is in the time column, you're going to just do each half-life rate, depending on the isotope. And you just keep going by the set rate of the half-life until you get to your final time. So for this example, if our half-life is 1,600 years, we're just going to increase in increments of 1,600 years. So go to the time column, and we write our next number of 1,600. So 1,600 years have passed. In the mass column, the only thing you do is just divide whatever you had in the row before it. You're going to divide that number by 2. So if our previous number was 8,000, we're going to divide that by 2 to get 4,000. Now, we need to do another half-life. So 1,600 years pass again, and that will give us 3,200 years. And the next and final task is to take 4,000 and divide that by 2. So that gives us 2,000 atoms remaining after 3,200 years have passed. So the answer to our question is, How many atoms will remain after 3,200 years? 2,000. Now, sometimes it might ask you, well, how many half-lives have occurred? You might be tempted to write 3 because in each column you have 3 numbers, but that's not true. The easiest way to devise half-life is to take an arrow and draw each of your half-life rates. So basically you draw an arrow from the 0 to the 1600 and the 16 to the 3200. The number of arrows you have is the number of half-lives that have passed. So it's not 3, but rather it's 2 half-lives, because you don't count where you started. The half-life is the passage between the two numbers, not the two numbers itself. So that's basically how you do a half-life problem. Now, we'll do another one just for security. So let's try a different style. Okay. 15. Let's do 15. So how long does it take a 100-gram sample of AS81 to decay to 6.25 grams? And for this one, you're going to have a chart that has your half-life values. So for AS81, it's 33 seconds. So what we do is we identify our 4 variables, and one of them will be unknown. So your final time, your time of half-life, your initial mass, and your final mass. Okay. How long does it take a 100-gram sample? So your initial mass, 100 grams. So like I said, this value is listed in grams instead of atoms. Your final mass, we're trying to get down to 6.25 grams. Your time of half-life is 33 seconds. And then we don't know how long it's going to take, so we have to figure that out. So we go and we do our chart. You can always just do these on the second page where you got extra space, but I'm just going to do it here. So again, time, mass. Time starts at 0. Mass will start at whatever our initial mass is, which is 100 grams. Okay. Now, 33 seconds is our half-life. We're trying to get down to 6.25 grams. 33 seconds pass, and we get down to 50. Another 33 seconds pass, which would get us to 66. We're now down to 25 grams. 99 seconds, and that would be 12.5. And then another 33 seconds pass, which would be 132 seconds, and that would be 6.25. So we were trying to get down to 6.25, so we have solved our problem. So it takes a grand total of 132 seconds to get down to 6.25 grams. How many half-lives is that? Just out of curiosity. Again, draw your arrow. 1, 2, 3, 4. So it took 4 half-lives to get down from 100 grams to 6.25 grams. So that's 2 examples of solving half-life problems. So go ahead and knock the rest of these out if you are a little bored and you want a challenge.